Okay, when constructing a confidence interval, we need to realize that, for example, a 95% confidence interval isn't perfect. And the idea is that if we were to widen that confidence interval, yes, we would be more confident in our answer, but usually at a cost. So when we calculate a 95% confidence interval, again, this is the formula that we use for confidence intervals, estimate plus or minus margin of error. So if we were in the magic mean activity, we use as our estimate the 240.79, which is our mean of our sample, and then we added to it 2 standard deviations to the right, which was 2 times 5, and subtracted 2 standard deviations to the left, which was subtracting 2 times 5. And this leads to a more general formula in that it's our statistic that we get from our sample, plus or minus the critical value, which is the number of standard deviations above the mean or below the mean that we want to be, times the standard deviation of the statistic. And this is the formula we're going to use to create all of our confidence intervals. So please include this on the note sheet for a general formula for confidence intervals. So the confidence interval for estimating a population parameter would be your statistic plus or minus your critical value times the standard deviation of the statistic, where we call the statistic the point estimator, meaning that's our mean of our sample or proportion of our sample, and we're going to use that to estimate what's going on with the whole population. So a couple things you need to be aware of is that the margin of error, which I use a lot in the AP exam, is this part of our confidence interval formula. It's the part after the plus minus sign. So in this case, it's the critical value times the standard deviation of the statistic. So please record this on your notes. Okay? So we will choose our confidence level and the margin of error that follows from this choice. The critical value will depend on the confidence interval. So for example, if we do 95% confidence interval, our critical value would be around 2. Turns out it's 1.96. If we use a smaller critical value, say 80%, then we're going to have a smaller critical value. Again, our table of values will give that to you. The standard deviation of the statistic will always depend on our sample size. The bigger the sample size, the more precise our answer is, the less variation, the smaller your deviation. So if you look here are 2 pictures here of confidence intervals. And if you notice, the 80% confidence interval is much smaller than the 95% confidence interval. The idea is if we make it wider, we are going to be more confident that we're going to catch our true proportion. But that usually comes at a cost. People aren't willing to pay, sometimes aren't willing to pay for that 95% confidence interval, even though there's more precision in that answer. Okay, so the margin of error will get smaller as the confidence level decreases and as the sample size increases. These are the 3 conditions to be able to use a confidence interval, and later on when we get to inference testing, it will be the same conditions. So this is definitely worth memorizing. And again, please record this on your notes under the 3 conditions for calculating a confidence interval. The first thing is your data should be random. It should always be a simple random sample of data that you've collected. The second other thing is your data should be fairly normal. And we were looking at the penny activity and realized that if the sample size gets really big, then the data will be normal no matter what. And it turns out that that value is, again as a reminder, n has to be greater than or equal to 30. For sizes less than 30, we actually have to check to make sure the data is normal by usually making a graph and then actually physically inspecting the data, which is a lot more work. So the idea is that if the sample size is big enough and greater than 30, we can say the data is normal. For proportions, we use the 2 conditions where the number of successes, which we define as n times b, has to be at least 10, and the number of failures also has to be at least 10. So n times 1 minus b have to be both at least 10 for us to be able to say that the data is approximately normal. So again, for means, that means quantitative data. For proportions, that means categorical data. So 2 different conditions depending on what type of data you're dealing with. The third rule applies, doesn't matter which one. If you're doing random sampling without replacement, your sample size cannot be more than 10% of the population. I.e., I call this the rule of 10. And the idea is if you take your sample size and multiply it by 10, you have to show that that is smaller than whatever the population size is. As long as you can guarantee that that will happen, then the independent condition will have been met. So again, record these 3 on your notes.